Euclid's Elements, Book 2, Proposition 10. If a straight line be bisected and a straight line be added to it in a straight line, the square on the whole plus the added straight line plus the square on the added straight line is equal to twice the square on the half plus twice the square on the half plus the added straight line as on one straight line. Got our original line, whole line, we'll call it AB, and we'll bisect it at C, and then we'll add on to it BD. And what we're going to say is that A, the square on AD, plus the square on AD plus the square on BD is equal to twice the square on AC plus twice the square on CD. Step 2, we draw from C using Proposition 11 of Book 1. We're going to draw from C a line, call it CE, and we'll connect to AC, and we draw it perpendicular. That's from Proposition 11, so EC is perpendicular to line AD. We're going to connect EA and EB. And also what we're doing with line CE is from Book 1, Proposition 3, we're going to make CE equal to either AC or CB. They're equal to each other, so AC or CB. And then using Book 1, Proposition 31, we're going to create two parallel lines. We're going to create a line from D parallel to CE. We'll draw that like so. And then we'll draw a line from E parallel to AD, meeting that line there. We'll call this point G up there. And so we've created line GD parallel to EC and line EG parallel to AD. Okay. Now we know from Proposition 29 that the angle DGE and CEG are going to be equal to two right angles. We can say that angle CEG plus DGE equal two right angles. Therefore, the angles BEG and DGE must be less than two right angles. The angle BEG plus the angle DGE, equal, we'll say, I'll just write it out, less than two right angles. And that being the case, we know that if we extended line GD and extended line EB, that they would meet. So we extend them down until they meet. Fix this up a little bit. And we'll call this point F right here. And then we are going to connect A to F as well. A to F. So I won't say that. That was postulate 1 to connect A to F. And then we just know from postulate 5 that GD of Book 1, that GD and EB would meet at point F when they were produced, or at a point, and it turns out to be point F. Okay, now, if we look at the triangle ACE, we know that we've got the right angle here, and we know these sides are equal, that one as well, and therefore from proposition 5, we can say that the angle CAE will be equal to the angle AEC. And because of proposition 32, since the angle ACE is right, then these two angles must equal one right angle. So CAE equals CAE plus angle AEC equal one right angle. But since they're equal, as we just showed in step 6, therefore each of them must be half of a right angle. So each of these is 1/2 of a right angle. I'll draw that in right here. Similarly, with triangle ECB, we can prove that the angle CEB and EBC are both equal to 1/2 of a right angle. They're each 1/2 of a right angle. There. And I'll note this right now. So we can see that the angle AEB, since we've got half a right here and half a right, the whole angle AEB, or we'll call it AEF, is a right angle. That'll come in useful later on. AEF equals a right angle. Step 10. Now we can also look at the triangle BFD. And we know from proposition 15 that the angle, prop 15, we know that the angle EBC equals the angle DBF. And we know from proposition 29 that the angle FDB, I'm going to draw it in as a right angle. We know that it's the alternate angle to the angle ECD. So because GF is parallel to EC and they've been cut by transversal CD, therefore the angle FDB is equal to the angle ECD, and because it's a right, then the angle BDF will be a right. Therefore, angle FDB equals angle ECD. And because this is a right angle, therefore this one is a right angle. And now we can utilize proposition 32 again for this triangle. Because this is a right angle and this is half of a right angle, then the remaining angle BFD is half of a right angle. The angle BFD equals 1/2 of a right angle. So I will put that marker in there. Now if you look at triangle EGF, we know that the angle at G is going, because the figure ECDG is a parallelogram, we made it that way, CD parallel to EG and DG parallel to EC, and we know from proposition 34 that opposite angles in a parallelogram are equal. Therefore, the angle at G is equal to the angle at C. So angle G equals angle C, and they are both right angles. But we know in the triangle EGF, this angle down here was equal to half of a right, and since that is a right angle, then by proposition 32, the angle GEF is also a right angle, or half of a right angle. So proposition 32, we know that angle GEF is half of a right. And then we can fill in our last. So all of the angles that are marked in red here, 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 they're all equal to half of a right angle. Also, going back to this triangle, BDF, we can show via Prop 6 of Book 1 that the side BD will have to be equal to the side DF because they subtend the equal angles. So by that proposition, side BD is equal to the side DF. Okay, let's go back to our triangle ACE. We know that AC is equal to CE, and therefore the squares on them will be equal. Therefore, the square on AC is equal to the square on CE. But that means the two of them together will be greater than the square on either one of them. Therefore, AC plus the square on CE equals twice the square on AC. But by proposition 47, we know that the square on AE is equal to the squares on AC and CE. EA squared equals AC squared plus CE squared. And therefore, by common notion number 2, the square on EA will equal twice AC. The square on AC. EA squared will equal twice the square on AC. And we can do the same, similarly, we can do much the same with the triangle EGF. We know that FG and EG are equal because those sides by proposition 6 subtend equal angles, so that we can say GF squared plus EG squared, or sorry, equals EG squared. And then if we take both of them together, they'll be twice one of them. Equals twice EG. Good. Now, well, actually, I'll say this right now. EG, we know, is because opposite sides in a parallelogram are equal, EG will equal CD. So we can replace twice EG with twice CD. And we can do that by proposition 34. Yeah, so that was for that step there, step 22. Therefore, we can say, we know that EA is twice AC. Oh, wait, I skipped a step. We know that the squares on EG and GF are equal to the square on EF, and that's by proposition 47. So proposition 47 says that EF squared is equal to EG squared plus FG squared. But we can see that twice the square on EG was equal to EG squared plus GF squared. Therefore, by common notion number one, which I think was what I should have had up here. I think I said common notion 2. Common notion number one, things equal to the same thing or equal to each other. We can say that EF squared will equal twice the square on EG. So EF squared will equal twice the square on EG. Step 24. We're going to combine this step right here, I'm going to check off, and this step right here. And we're going to use, instead of EG, we're going to replace this with CD like we did right here. So I'll say twice CD. So we're going to combine, technically, combine the two check marks right here. Therefore, E, the square on EA, plus the square on EF, equal twice the square on AC, plus twice the square on CD. Now, we said that the angle AEF, right here in step 9, we said the angle AEF was equal to a right angle. So that would make the triangle AEF a right triangle, which means that the square on EA and the square on EF are going to equal the square on AF. So I can rewrite this and say that they are, by proposition 47, I can replace that with AF squared. And we'll just bring this side down. So twice the square on AC plus twice the square on CD, step 26. But we know that the triangle ADF is a right triangle, and therefore we can apply proposition 47 again. And we can say that the square on AD plus the square on DF is equal to the square on AF. So I'm going to replace AF with AD squared plus DF squared equaling twice the square on AC plus twice the square on CD. Step 27. But because of the step where I showed that BD and DF are equal because they subtend the base angles, proposition 6, we can substitute DF or substitute BD in for DF. We'll rewrite this line now as square on AD plus the square on BD equals twice the square on AC plus twice the square on CD. But AD is the original whole plus the added straight line, so that's the square on that line. BD is the square, this BD squared is the square in our added straight line, and then twice AC matches up over here, which is twice the square on the half of our original, namely twice the square on the half of AB, plus twice the square on the half of the original line, plus the added straight line, which is CD. So this line right here is the same as what our to prove was, and we're done. Q